Hi everyone, nice to see you all here again, and I would like to take you with me on a journey that lasted about 8 months and that resulted in going very deep in the internals of one of the most modern smartphones nowadays. So until recently I was a principal security analyst at a small Dutch company called Riscure, where I'm specialized in trusted execution environment and security systems of modern system on chips. And this journey started in October 2021 with Google releasing the Pixel 6, a new generation of smartphones designed around custom silicon and with security as one of the main selling points. And as having quite a personal but also a professional interest in these type of systems and the security components powering these type of devices, I was immediately interested and decided to take a look at. And let's now jump 8 months forward to August 2022. Android 13 was released, and this was with a message that if you would install it, you would not be able to go back anymore to Android 12. The reason was that there was a critical vulnerability being fixed, and the anti-rollback counters were bumped to make sure that devices would no longer be vulnerable after installing the patches. So, what has happened in between? Well, let's start with giving a very quick overview of how the software stack looks like on a Pixel 6. And of course we have our standard Android environment with applications and a Linux kernel underpinning it. But we have an entire second world living next to it, consisting of extra operating systems, extra applications, and all kinds of firmware that are making sure that this is all working together. And the Android world, we call it the non-secure world or the non-trusted world, and we call the other side, we call it the secure world or the trusted execution environment. And here we have an operating system called Trusty. We have a secure monitor, also called BL31, from the component name of the open source ARM Trusted Firmware Reference project that is orchestrating the switching between the secure and the non-secure side. And we have the loadable firmware, which is effectively a collection of drivers, but that is an independent blob in the system. So Trusty is the TE OS that is used on this device, and it is based on Little Kernel. And Little Kernel is an open source project which is probably best known for its usage in bootloaders, etc. And Trusty is built on top of it, and it's also an open source project. And it is already quite old. I don't know exactly how old it is, but when I started looking at trusted execution environments around 2015, it was already around as a reference implementation. To my knowledge, this is the first time it is actually being deployed on a Google phone as a production trusted execution environment. And one of the interesting characteristics of Trusty is that it is a pretty well hardened TE operating system. It has, for example, it tries to run everything in user mode, including drivers. It uses strict access control lists to determine what drivers and applications can access, and we have a nice set of mitigations beyond the standards like ASLR, but we also have control flow integrity and shadow stacks. And that will actually be one of the more interesting aspects that we will see later. So the way we talk with the TE, the secure world, is through so-called secure monitor calls. So let's say the Linux kernel would like to do an operation in the secure world. It will then issue a so-called SMC instruction, and this will make sure that the hardware will actually switch to execute from the secure monitor, and the secure monitor is the component that routes these requests to the right component that will handle them, but also allows the secure world to switch back to the non-secure world. And the way this works is that we have something called the runtime service dispatcher, and this runtime service dispatcher is effectively an array with services we have associated with certain ranges of SMC IDs. And then we have in memory somewhere a table with this is the IDs we can handle with this handler, this is the name, this is the function pointer that you have to invoke when you encounter such a secure monitor call. And inside inside an implementation derived from the open source reference implementation, we have some standard services, but we can also add custom services. For example, in this case, we see, for example, handlers for calling the Trusty operating system, which are implemented from the routing level from this runtime dispatcher. So if the Linux kernel wants to communicate with the trusty operating system, we will go through the secure monitor. The secure monitor will actually switch to trusty. It will jump to the starting point of trusty and say like, hey, I have a request here for you. Can you please handle it for me and let me know what I should return back to the Linux kernel? So the way this is implemented in Trusty is that we have 3 tables of secure monitor calls that it can handle. We have the so-called fast calls, we have knob calls, which effectively do nothing, and we have so-called standard calls. Fast calls are effectively atomic operations, like what is your Trusty version number? Do you support this version of the API? Please set this configuration bit. Standard calls are more operations that have to be scheduled. For example, I want to run this application, please execute this command for me in this application. This is something that can be interrupted, and thus that has to be scheduled by the operating system scheduler. So it doesn't necessarily complete in one time slice. We will for now focus on the fast calls. They are just, you do an invocation, and in the same run you will get back the response. And there is, in memory, there is a table by the fast call dispatcher that will actually contain all the fast calls that are implemented by the trusty operating system. And there is one particular fast call that at some moment in time was catching my eye. It is the request FIQ fast call. And this fast call is for routing interrupts to either the secure or the non-secure side, and how the interrupt controller gets configured for the routing of these relevant interrupts. And if we start looking at the source code, what we will see that in the handler is we will get 2 arguments. We get the FIQ, which is effectively the ID of the interrupt that we would like to configure, and whether or not we want to enable it. Then we reconfigure the interrupt controller with the state of how this interrupt should get routed. And then we will actually track in the global state like, hey, what is the current configuration of this interrupt? And the way this works in Trusty is that we have a global array enabled FIQ mask that will keep track of the status of each interrupt, whether it's enabled or not within this specific, at this specific moment in time. And we have a function that allows us to effectively set or unset specific bits in this array, because it is implemented as a bitmap where each individual bit is corresponding with an interrupt or FIQ ID. If you look at it from the native side, you see something interesting. First, all the functions are very aggressively inlined, which is in this particular case quite convenient, but there is also something that might be missing here. If you highlight all the usages of the FIQ idea, you see that it will calculate the address inside the interrupt controller. It will manipulate the interrupt controller accordingly. It will calculate the address of the enabled FIQ mask that it should manipulate by setting or unsetting the responding bit by whether you are enabling or disabling this specific interrupt. But there is one particular thing that is missing. This interrupt ID is never getting checked. So at least that is how it looks like. So let's try. So for this type of research, I start with an unlock bootloader. I make sure that I have a root shell, I can load custom kernel modules, and I have a set of tooling that allows me to peek and poke directly in physical memory, as well as some tooling for issuing arbitrary SMC calls. In this case, it's not about compromising the Android environment, although on these devices you could also have used the dirty pipe vulnerability, and then also effectively load your kernel module. So in this case, I have a nice command line utility called SMC, and the first argument is the SMC ID we would like to invoke. In this case, BC000002 is the ID that corresponds with the request FIQ command. So the moment we will issue inside the kernel the SMC instruction with this as the ID, it will get routed to the handler that we have seen before, and the following arguments are the FIQ and the whether or not to enable bit as arguments. So in this case, the FIQ is 1, 2, 3, 4, 5, 6, 7, 8. So what happens if I press enter? The phone reboots, and when the phone comes back up, conveniently it's logging also what's happening in the secure world in the Linux kernel crash log due to a nice logging driver that is there. And we see that we have actually a data fault that occurred on the secure side. And this data abort that we will see is that it tries to read from some unmapped memory with a very weird address. This basically confirms that we can control the array index, we can manipulate bits this way, set or unset them, and this will result, if you give some crazy number, in that we crash the system. But can we actually do something useful with it? Well, we have an array index out of bounds. It allows us to set and unset individual bits. So it's actually a nice data corruption primitive, right? However, if it was just that, I would probably not be standing here, right? So this thing also reconfigures our interrupt controller. And this interrupt controller is effectively a block of hardware that will respond on requests coming in through its register interface, and it is then configuring internal routing mechanisms accordingly. What also means is that if you will send requests to the hardware that it is absolutely not expecting, it's very likely you will either crash the hardware, cause hangs, trigger reboots, all kinds of weird side effects that will make exploitation impossible. And we should still not forget that we have a nice set of exploit mitigations. So what can we do then? Well, we have our global array, and how do two things look like in memory? I started to map out, based on the open source code, correlating it with the binary to see what the purpose is of all the globals, and I've been able to identify most of them. And one of the things that immediately caught my attention was the threat list. Can we maybe modify the threat list in such a way that well, maybe we can insert an additional threat. The problem is this threat list is effectively only the node head, and it doesn't really seem to be used after bringing up the system. So the threat list by itself doesn't seem to be very useful. The next thing that caught my attention was a structure called the idle threads. This is effectively the operating system threads that are running the busy loop for the standard calls, waiting for the next request. So it is sort of implemented as an endless while, waiting for the next request to come in, and then it will schedule it on another thread where it will execute a standard call command. But the busy loop is running on the idle thread. And this gives us direct access to the relevant thread structure, which contains all kinds of interesting information that we will see later. But also this one was not very promising. It only resulted in crashes of the system. It was apparently not possible at the right moment in time to affect the right part of the thread structure, or the offset was already getting so big that we were simply crashing the interrupt controller because it got so confused that we were effectively doing a hardware out-of-bounds access. Then I saw a different table, the interrupt handlers. So there are two sets of interrupt handlers that when the hardware sends an interrupt to the operating system, it needs to associate what code gets executed when you are handling that specific interrupt. And each interrupt that the system supports has its own handler. And the structure that is handling describing which interrupt handlers there are is effectively a function pointer together with an argument pointer that we can provide to the function that needs to be invoked. However, while it would have been nice if we could have put here a random address and maybe start a code chain that we would like to execute, we have control flow integrity. And what that effectively means is that just before our handler gets executed, all pointers get validated against a list of known handlers that we can invoke this way. And this is effectively implemented as a branch table where for each of the handlers we have one branch to the specific destination, and with a little bit of bit matching we can check like, hey, is this a valid branch destination? Is it not a valid branch destination? Let's panic the operating system. And this is used to effectively protect all function pointers in the system, which is something that is quite effectively. So this was still not really going anywhere, but we still have this argument pointer, right? So can we maybe do something with this argument pointer? So if we look deeper at which interrupt handlers are supported, there is effectively only one interrupt handler that is taking effectively an argument, and it's the UIRQ handler. And the UIRQ handler is taking a handle to some data structure, and this handler is used for implementing user mode interrupts. So what will happen is some block of the hardware sends an interrupt, let's say an SPI controller or a mailbox, for example, in the system. It will send an interrupt, and we would like to have the handling of that in user mode because we want to reduce the attack surface. So if we start looking at how this interrupt handler is being implemented, we see that it is effectively a single function call to the event source signal function, which takes this handle as an argument. And if we start following this handle, we actually see that it is a chain of pointers to data structures which are related to event handling. And effectively an event is, for example, I want to wait for an incoming interrupt. And then we have an event source that is effectively the event handler that says, I have here an event for you coming from me, can you handle it? And then we have a wait queue that is effectively a list of threads that have subscribed to that event waiting to happen. So these threads that are waiting are effectively idle, they are suspended, and they are waiting for this interrupt to occur. So in this particular case, that would be the driver that has subscribed for this specific interrupt. It's now suspended, and it's waiting for the interrupt to come in. What is interesting of the wait queue is that we have a list, and a list, well, based on the data structure, it's not immediately obvious what it is. But when we start following where these lists are actually point to, it is actually a data structure within the thread structure. We have a queue node within our thread structure where this list is pointing to. So our wait queue is actually having this list of threads that are being waiting, and by just following that pointer, we have found our thread structure. And inside our thread structure, we have also the complete saved state for when a thread gets suspended, including the stack pointer where the data of this particular thread is actually being stored, so that when the thread needs to be scheduled again, it can restore all information from the saved thread information. So if we now follow the call chain, we have event source signal, which will do a notify for that particular handle, which inside the notification, we will see what the event is that corresponds with that particular handle. We will do a signal of that the event has occurred. When the event is signaled, we say to the wait queue, hey, can you please wake all threads that are waiting for this particular event to occur? And then inside the wait queue handler, the waking function, we will actually see that we will go over all the relevant threads, mark them as ready, and in case that we can immediately reschedule the thread to be running next, we will say like to the scheduler, please make sure that the moment our interrupt handling has finished, that this is the next thread that will start executing. So effectively, this is a primitive that allows us to schedule a thread. But where are these threads coming from? Can we maybe create a fake thread in the system? Because so far I have not seen a single check that a thread has to be a thread. So how does context switching work in Trusty? So what we have is a function called the thread reschedule, and this gets called at several moments in time. For example, your TA has running for too long, and the scheduler has decided that it is now time for another TA to run, like with a time slicing mechanism. It could be that the TA has indicated themselves they would like to yield the execution, and it is time for another thread. So there are several moments a thread can get rescheduled, including when we have the wait queue event occurring and say like, please start all the waiting threads and make sure they start executing now. And while it is doing all kinds of bookkeeping for the scheduler, there is one particular function that is of interest for us. There is something called the architecture-specific context switch function, which is effectively taking two stack pointers, saving the register state from the old thread to the stack, and restoring the register state from the new to be executed thread from its stack. And this is just a normal function. It will load its return address from the saved stack, and it will return to that. And normally what it will return is to a caller of the thread reschedule function, and at its end it will do some further bookkeeping, make sure that the relevant locks get released, to make sure we will not end up in a deadlock of the system, but we will also make sure that the shadow stack gets enabled. As I mentioned before, they have shadow stacks, which effectively means that all the return addresses are stored on a separate stack, which is being tracked in the register x18. So our thread structure contains all the relevant information for storing and restoring the execution of a thread. And if we want to make a payload out of that, we could do that by making sure that we have the tail of the thread yield function, the register state that we would like to reload into the registers, together with the shadow stack that will contain the ROP gadgets that we would like to execute. And in this particular case, I went for a small hello world payload, as it was a nice way to see that code execution would be feasible. So our thread yield will load the first return address from the shadow stack, which is gadget 1. We want to control x0 to be able to call the printf function. This gadget will then return to a call to printf, and this particular call to printf is part of the initialization chain where we don't have shadow stacks yet. So interestingly enough, the very last address of the ROP chain is back on the normal stack, which is a call to the thread exit function, because by making sure we mark our thread as finished, we can make sure that the system is not crashing. If we would randomly crash the system, it's also immediately game over. We can execute a ROP chain once, but we cannot do it multiple times, and that is inconvenient. So how do we then get code execution from here? Well, just having the data structures in memory, remember we can flip bits, so we can make the data structures in memory, is not going to give us code execution yet. So what we need to make sure of is that our data structures are actually being used, that the interrupt handler is getting invoked with as argument the handle pointer that will point to the first data structure of our chain, the event source structure. So we have, as I said before, among others, timer events like, hey, it is time for a different application to start executing, or it is time to switch to a different thread. This is handled by the API reschedule handler, and this is effectively a mechanism where cores can signal to each other which is coming from the interrupt controller. What I effectively do is I replace the normal reschedule handler with the pointer to the platform UIRQ handler, together with the argument, the handle pointer as the argument. And then I simply do something, an operation that will take long enough to complete to make sure the reschedule handler is getting invoked. And what I have found is that on an ADB shell, the longest command that you can easily invoke from the normal world is generating a new key. I don't care about that key. The content is completely not relevant. It's just a nicely long-taking operation that will make sure the reschedule handler will get started. And then very importantly, make sure that the original reschedule handler gets restored, because otherwise the system will end up in a very big mess and you have a crash in a matter of seconds. What about ASLR? Because I said, well, there is also ASLR. Everything is randomized, actually pretty aggressively in the virtual address space of Trusty, but not Trusty OS itself. So conveniently, the whole global data structure can be found. The code is at a predictable location, so no information leak is needed. And I would like to demo this. So I have here a Pixel 6. It is running the original factory image from August 2021. Let me get a root shell. I would like to monitor the kernel log for Trusty log messages. Also here. And I conveniently wrapped everything in a script. And basically it starts printing hello from Trusty. What's good to remember here, every time you see here hello from Trusty, it's again getting code execution on the secure side. And I can do it again, and we will print a few more times. So each time it will inject a new thread in the system, it will execute the small chain that you have seen, and yeah, basically now I can print messages. Of course, I can go further from here. We could, for example, attach a mem copy to the chain and get some data in or out. But I don't think that's the more generic post-exploitation. That is not the most interesting bit, because I would like to dig deeper. So, let's dig deeper. So far, we have been talking about the secure world and the non-secure world. So I would like to give you an introduction to secure memory and how this all works. So we have our normal CPU, also known as the application processor, because in a modern system on chip we don't have one CPU, we have many CPUs. So let's refer to it to the application processor. And this application processor can either run in secure or non-secure mode, and when it wants to access the memory, it will actually, through a hardware path, will talk with the memory controller, and the memory controller will access the DRAM. This is of course a huge simplification of how it all works, but the important thing that you need to know is that there is somewhere in a piece in the hardware, and let's say for the sake of simplicity that this is part of the memory controller, we need to have a component that says, well, is this memory access allowed, yes or no? So let's say we want to access some memory and everything except where the secure operating system is living, well, the application processor in the non-secure mode can access it. And of course the secure memory we cannot access because, well, that would not make sense. But there are also other types of memory. So let's say we also have something like a video buffer. Well, if that is just a normal video buffer, let's say you are playing a random video from a website, there is no reason to protect this memory, so we can perfectly access it. But there are also special types of video buffers. Let's say you are watching some high quality premium content, and this is protected. Well, in that case, your video buffer is also protected, and it is actually being part of the secure memory, and the non-secure side of your application processor can no longer access the secure video buffer. Of course, when we would switch the application processor to a secure state, it will be able to access the secure video buffer. But there is more. So we have our application processor, we have our memory controller, but we do this through a bus inside the chip. But not only the thing that is connected to the bus is the application processor. We have actually a whole bunch of other things connected to the very same bus, and all those things can also make accesses directly to the memory. In a modern chip, this can easily be tens, if not hundreds, of engines that directly have ability to go to the memory themselves. A few examples, your flash controller, your USB controller, but all kinds of other auxiliary CPUs that are within the system. And of course, these engines need to be controlled, which goes through another bus, also known as often known as an APB bus. However, of course, we want to isolate things, right? It would be a bit weird if all those engines just randomly can access memory and effectively compromise your system. For that, we have I/O MMUs. These are effectively, it's the hardware peripheral version of the MMU you have in your CPU. Which means that effectively every hardware block has a set of page tables that dictate which part of the memory is accessible by that part of the hardware. But we are not there yet. While most of these hardware engines will never have a need to go beyond non-secure memory, there are actually some hardware engines that have a switchable state. They can either do memory accesses in a non-secure state, but they can also do memory accesses in a secure state. This effectively means that you are giving a part of your hardware access to the secure memory buffers. So let's start with a normal media pipeline. We are just playing a random video from a random website or a video player app with some content. And on modern CPUs, a lot of this is not happening in software. This is actually all happening in hardware. So while we have the video player that is effectively getting the content that needs to be played, all the processing and decoding happens by hardware engines. And there are several steps that need to happen. The most important part is, of course, decoding the format in something that the hardware can understand. But then we have all kinds of post-processing steps for like the color, for mixing different things, so you can actually have a part of your user interface on top of your video and other things that we need to do. But eventually, after several steps, we will get to the display hardware. And this can be the hardware engine that is driving the display of your device, but it could also be an HDMI port or another form of output where the content is or where it is being shown. What is good to remember, these are hardware DMA engines, what effectively means they can access the memory independently if they are being told so to do. But if we want to make a secure media pipeline, that effectively means that a part of the processing happens on the secure side. Most notably, the content will be decrypted, will get decrypted on the secure side. And now all the hardware engines need to make sure that the decrypted and processed and decoded content will never leave a memory buffer that is part of the secure memory, because otherwise it would leak the content to the non-secure world. And there is one particular engine inside these chips that is doing the decoding step of this processing. And this is called the MFC, the multi-format codec. And it is effectively an ARM CPU running a pretty serious blob of firmware that will get the encoded media and decode it for you in the raw media stream, for example, a video stream, an audio stream, or whatever content you are consuming. So this MFC, it is a separate CPU in the system. It is a little ARM core, but let's say it is in the non-secure mode and it wants to access the memory. Well, if it would have unrestricted access, it could be used, for example, to compromise the Android environment, which is something we don't want. So the I/O MMU will selectively map only a part of the memory in the address space of the MFC. So the video buffer that where it is actually fetching the content from, or where it will write the decoded content, is, for example, non-secure. It will fetch the page table from the non-secure page tables, and then the memory controller will happily say, hey MFC, you are allowed to access that block of the memory. In the very same way, we cannot access the memory even when it is mapped in the I/O MMU if it is secure memory, because the MFC has a non-secure state. But now, let's say we switch the MFC to a secure state, which is effectively, we switch some registers within the hardware, and now magically we are no longer using our non-secure page tables, but we are using a second set of page tables, the secure page tables. And now, if the secure page tables have this video buffer mapped, the memory controller will say, I am happily giving you access to this video buffer. So, what do we know about the MFC? As I said, it's a 32-bit ARM core running some nice firmware, but beyond that, very, very little is known. Effectively, there is no documentation about this thing, except what you can find out from the drivers that are part of the Linux kernel. It can switch between a secure and a non-secure state, but it's not the only engine that can do that. There are quite a few engines that have this capability, and there are actually drivers for switching these engines between a secure and a non-secure state. For example, a 2D engine, a 3D engine, the JPEG decoder, and, well, it's an insignificant number of other engines as well. This MFC, it is a CPU, but the application processor will control it through a register interface together with a mailbox to which the application processor can send commands to the MFC, and the MFC can send requests back to the application processor. And one thing of particular interest here is that what you often see is that, most likely for performance reasons, is that even when such engine gets switched to a secure state and it has access to secure memory, it is still the application processor in non-secure mode that will do all the interfacing. So the application processor in non-secure mode has still access to the majority of the registers, like the command registers, the start-stop registers, the mailbox. So it's still the non-secure side that is actually asking the MFC to do things. And of course, memory accesses go through the I/O MMU. The Linux kernel will manage the non-secure page tables, and there is actually the blob of drivers I've talked to you before that is running alongside Trusty OS, the DRM loadable firmware that is actually managing the secure page tables. So if we look at it a little bit from a schematic way, we have our MFC that is able to do memory accesses through the bus to the memory controller. The application processor can access through the APB bus the register interface of this MFC engine. This has things like a reset, like please forget everything you know, hardware, go back to the initial state. Are you actually executing right now through a status register? It has things like from which address should the firmware start executing. You can, for example, start the engine through the register interface and have it actually getting a clock signal, so it will actually start executing and fetching instructions. And we have the mailbox, which is effectively, it's the best way to see, it's not really how it is implemented in hardware, but the best way to see it is as like in the region with the hardware registers, we have a tiny bit of memory that both the application processor and the MFC can see, and that we can use to exchange some information. I think in the particular case of the MFC, it is in the order of a few kilobytes of memory that we can actually access from both sides, and that can be used for exchanging information. We have a protection controller that we can actually also set, like, do we want to have these registers and the mailbox being accessible from which part of the system, which could be used, for example, to block access to some registers or from some parts of the system. So what kind of registers do we have? Well, technically we don't know. This is not documented. There is no documentation of it, but the Linux kernel driver is actually very helpful. It is helpful naming what kind of registers we have in the hardware. For example, there is an on register, or there is a RISC-to-host interrupt register, which is apparently to send a message or to indicate from the NFC back to the application processor, like, hey, can you please take a look? Something has happened. And when you start reverse engineering the firmware of the MFC, you will immediately notice that there is not a single string to be found. I don't think there is, well, maybe there are 10 in a few hundred kilobytes of code, so effectively nothing. But luckily what you see is that the register interface and the mailbox interface are actually largely the same on both sides. So we can actually, based on this information, start reverse engineering. And while on the application processor there is some offset where these registers are being mapped, what we see in the firmware is that this is actually getting mapped at C0000000, which is quite nicely standing out from the rest of the firmware. So by correlating the different pieces of information, it is possible to start to get an understanding, how is this MFC working, how is it having a view towards the rest of the system, how could we potentially start it, and how can we start to send messages and exchange information from the MFC back to the application processor. So let's now talk a little bit about the DRM loadable firmware. So this is a privileged component running alongside the Trusty operating system. It is effectively having the same privileges as the TE OS, and it is handling a very specific range of SMC calls, so that if the Linux kernel is issuing a secure monitor call with a number that is within that range, it will architecturally get routed to this loadable firmware blob. And this loadable firmware blob is effectively the one responsible for switching security states, managing the secure page tables, ensuring memory gets protected when it becomes part of the secure memory. So let's say we want to map in a buffer for decrypted video content so the MFC can start processing it. You have to ask the DRM loadable firmware, hey, this is the memory you can use for that. Can you please protect it and make it part of the secure page tables? We have for this the secure monitor calls. Also those are not documented, but again, the Linux kernel driver is being very helpful, and there are a few secure monitor calls standing out. So we have, for example, the ppmp protect and unprotect calls, ppmp MFC firmware protect and unprotect calls, and the protection set SMCs. And that one is of particular interest. That is the one that is going to give an engine access to secure memory or not. This is the call that switches the engine, like, you are now no longer a non-secure engine, you are now a secure engine, and you are part of the secure world. So in this case, if we do a protection set command with the index 0, apparently that is corresponding with the MFC ID. Or if we use index 12, it is apparently the G3D engine, whatever that might be. So how does this MFC firmware get loaded? Well, also this is part of the Linux kernel. Apparently we first need to protect the relevant bit of the memory where we are going to load, or where we have loaded the MFC firmware. Which conveniently is describing also the data structure that we have to use for that. So we need to give, like, where is it residing in physical memory, how big is it, what kind of memory is this. We are in this case explicitly tagging it as like it is the video firmware that needs to get protected. How big is it, and like that. And then we call the special protection command for the MFC firmware that is part of the ppmp command set. And that will then actually making sure the firmware gets mapped in the MFC. The MFC is configured correctly, its start address is set, and it is effectively now ready to get started with the firmware we have loaded. But power management on modern chips is very aggressive. It also means that we cannot just load some firmware in a random CPU and leave it running, because that is the thing, that if you would do that, your phone would get super warm and you would start complaining that the battery life is maybe 4 hours. So we actually also need to be able to undo the same procedure. It needs to be possible to unload the firmware, stop the MFC, make sure it enters a very low power state and effectively is clock gated to make sure no energy is being consumed when it is not being used. So for that, the Linux kernel driver has the opposite procedure. We first unprotect the firmware, we unmap the memory, and then we ask the power management hardware, like, can you please cut off the power to this domain because it's no longer needed. But don't forget, this is not your normal DMA engine, right? A normal DMA engine, we, for example, say, copy this from memory to that location in memory. It's this many bytes, please start now. And then the hardware will do that for you. And when it is finished, and it will not do anything on its own anymore. But this is a CPU. A CPU can pretty much, as long as it is running and it is not suspended, it can do what it wants. Of course, it is restrained by the firmware it is having, but we can unprotect the firmware. So the idea I had is, like, what happens when we unprotect the firmware when the NFC is switched to secure? So I started looking and what will happen, and this brings me to a part of the loadable firmware where the page tables are being managed. So what you have seen is we have those two calls, right? We have the MFC firmware unprotect and then the ppmp unprotect calls. The ppmp unprotect calls is for unprotecting the memory, and the MFC firmware unprotect is for unprotecting the MFC specific side of that. What we see in the loadable firmware in the function that is doing the unmapping of the memory from the secure page tables is that it is actually ref counting these page tables. So the moment you add something in memory, we will actually increment the counter and keep track how many things we have in memory. And when we have, when we are removing something from memory, we will also decrement the counter. But what really gets interesting is when the counter reaches 0. When the counter reaches 0, it will also make the memory where the secure page tables reside also getting unprotected. And these secure page tables are at a fixed location in memory. They are at E0, 0, 0, 0, 0, 0, 0. So the moment we have removed or unprotected the last piece of secure memory that is like dynamically getting switched this way, we unprotect our page tables as well. And that should be fine. There are no longer any valid mappings, so what could be the problem of that? Well, it started with, what if we leave the MFC running and when it is switched to secure? So let's just try. So as I said, I have the tooling for poking directly in the physical address space nicely from the command line. So I write 01 from the top of my head to the start register, and I get a crash in the crash log of the Linux kernel. And the Linux kernel said, like, hey, a page fault occurred in one of the I/O MMUs, or the system MMU as they call it. And this page fault occurred at address 0. And it was a secure interrupt. Okay, that's fishy. Normally you would expect to get non-secure interrupts, right? And the non-secure side driving some hardware, most likely the hardware is non-secure as well, because it should not be able to access secure memory. But in this case it was a secure interrupt. And it was an interrupt from address 10000000, which coincidentally is also the start address where the MFC starts fetching its firmware from. So apparently I have been able to switch the MFC to secure. I did not start it. I removed all the mappings from the secure page table. I didn't touch the MFC, so it's still secure. I write a 1 to its start register, so the MFC thinks, okay, I need to boot up, I need to start fetching my firmware. It tries to fetch the first bytes of the instructions of its firmware, and the secure I/O MMU says, well, I cannot do that for you because I have no corresponding mapping. But what also means if there is no corresponding mapping or no corresponding mapping at all, our page table is also not protected. So can we maybe do something with that? And that is effectively the second vulnerability. So how can we actually abuse this? Well, we want to load the MFC firmware, right? Funny enough, it doesn't have to be firmware. You just need to claim with the right size what the MFC firmware should be. It's somewhere there in memory. You switch the MFC to secure, and all the hardware gets configured correctly. You unload the firmware. Again, you do nothing. It's just that you tell the hardware, like, hey, you no longer have firmware now. The I/O MMU page tables for the secure side get unprotected, so let's overwrite it and make some fake entries to make sure that 10000000 is now actually mapping to a valid destination in memory. Let's put a piece of code there that we want to execute when we start the MFC, and we release the MFC from reset. And what we effectively want to do, so we know the location where it is fetching its firmware from. We know where the registers and mailbox are mapped in the address space of the CPU. This is fixed. This is not going through the I/O MMU, but they are always at the fixed location of C and 7 zeros. And we make an extra entry. And this extra entry is not some random location of memory. Let's now point it to the secure TE-OS memory, because maybe that will mean the MFC can actually access secure memory. So the very first piece of code I have used is a block of code for finding the secure monitor. And what you see is, as I discussed before, we have the runtime descriptor as part of the secure monitor. And there are in this ARM reference implementation that is open source, there are some standard services that effectively every implementation has. Like, what is your version number? Which also means that there is a number that is identifying the SMC range that corresponds with those services. You can effectively always find that number. And what I have found, that is also not, you will not have many other hits when you are looking for that number. So if we then look the secure memory where we have it mapped, and we match that number with the location in memory where we find it, we have found the runtime service function pointer table. What we then can do is we copy out that table. Can we do that? We copy out that table to the mailbox, and what the mailbox, because it is sort of shared memory between the MFC and the application processor, we can now see in the mailbox this table appearing, including all the addresses where those functions reside. So now we know where those handlers are. And the handler I am particularly interested in is the one that is handling SMC ID 80000000, which is, well, it is effectively just returning a constant. It is, I think, some version number or a feature number. You don't have a whole lot of room. You have only room for a handful of instructions that you can put there. But there is actually something that can put there that is very convenient. It consists of 7 instructions, and it is effectively a 32-bit read-write handler. So if we now put that little piece of code over the implementation of that if statement, what we now can do is issue SMC 80000000 and say, like, please write this value to this address, or read a value from this address for me. And you have effectively created a very convenient secure memory read-write handler. While the previous exploit was, or proof of concept was significantly more complex, the proof of concept of this one is actually fitting on the screen. Assuming, of course, we have the tooling for directly reading and writing arbitrary physical memory. But what you see here is effectively, we need to enable in the power management the MFC block. We need to claim where our MFC firmware is going to be in memory. We protect the memory. We say the MFC firmware is there, it is protected now. Switch the MFC to a secure state. Unprotect the firmware. Unprotect the memory. So now the reference count has reached 0 again, and the page tables have become unprotected, which means we can now touch the page tables, fake some entries in the page table to ensure we have the mapping of where our shellcode resides in memory and our view towards the secure memory. This is the payload for patching BL31. We put a marker in the mailbox so we can see when the MFC has successfully finished executing, and then we here set the start bit in the start register, like, please MFC start executing now. Anyway. And I would like to also demo this one. Let's go here, this one is still. So again, I have the root shell on the Pixel 6 here. I can actually show it to you. It is what I have described. It is just a script that is doing the corresponding commands. It is convenient if you do this on a root shell. I need to stop some services because otherwise sometimes some display thing suddenly thinks that it needs to decode an image or something, which is not very convenient. Oh boy. I have name. Oh. Now I crashed the phone because I used the wrong command. Okay. Mem is the non-secure side. I should have used BL31 mem for using the read-write handler. Shouldn't take long. Luckily, we still have a few minutes. NFC. What? Let's resort to the video and give me 2 minutes. Anyway. Effectively, I do the same. I run the script. I guess I should not have shown the script to you. So what you see here at the very bottom, it can be challenging to see, and I should have stopped it there. Oh my God. Why are you completely tripping? There. Okay. So. What you see at the very end is a little piece of secure memory of the logging buffer of the TOS initializing. Playing the video was more stressful than running the exploit, to be honest. Now we can access everything in the secure memory using our read-write handler. Yeah. So, the solution. So, of course, fixing just the vulnerabilities is an option. However, there is more. Actually, this chip also has a separate security core. So what actually has happened is that this attack has exposed several cryptographic keys, etc. And with Android 13, they have actually started to involve an even higher security domain within the chip for deriving relevant secrets for attestation and other purposes. Effectively moving those things now to the security core. And what personally interests me is that we slowly see stronger mitigations coming to the secure world. I found it very interesting taking a look at CFI and the shadow stack, but also using the hardware for actually leveraging in building an attack. And in this particular case, the security CPU was the rescue, and that way they could recover the security of the platform, which was launched in August last year, and this was why it was, among others, a mandatory upgrade to Android 13. Thank you.